Okay, welcome back to calculus. So today we are going to go ahead and talk about L'Hopital's rule. Now, in order to use L'Hopital's rule, you have to make sure that you be very careful that you actually have the conditions that you're allowed to use it. Okay, so every time you're going to use this, it has to be a fraction. Okay, you can manipulate it a little bit in order to make it a fraction, one fraction, but you're going to have effectively a f of x, g of x. You're going to have a limit. Now, your x can go to infinity, but it can go to any other number. Okay, so I'm just going to write an n there, but includes infinity. Okay, and if you have something called an indeterminate form, you plug in your value here. If it's 0, you're going to plug in 0 to both of these. 6, you're going to plug in 6 to both of these. But what you're looking for is you get a 0 over a 0, or an infinity over infinity. Okay. If you start not a fraction, if you get an infinity minus infinity, okay, you can also get a 0 to the 0, excuse me, or infinity to infinity. Okay, I don't think your book uses these, but they are also ideas that you can have. Then you can't cancel these. Okay, this here is not 0. Infinity of infinity, it's not 1. This is not 0. So what they call them is they have indeterminate form. When you're doing them, one of the things I check for when I'm grading is, did you check for indeterminate forms? So if I don't see like I got 0 versus 0, 0 over 0, infinity over infinity, and you say indeterminate form, then we're right. We can go on with the problem. But if you did not check the indeterminate form before you use L'Hopital's, then I'm going to mark it. You're going to get points off. So double check to make sure you have indeterminate form before you go off and use this. Okay, that's one of the things I absolutely check for. Okay, so here we go. The first couple of problems are pretty tame. They're kind of nice. There's a couple of them in here that are a little tricky. The other thing about L'Hopital's is if you use it and you plug in your values and you get another indeterminate form, you have to use it again. Okay, and so you do not have an indeterminate form. The limit may not exist. That happens. Okay, or you're actually going to get a value. Okay, but if you keep coming up with indeterminate forms, you have to keep going until you don't come up with an indeterminate form. Okay, you can use other methods of evaluating a limit. That's fine. Okay, but if you're going to use L'Hopital's, you check indeterminate form first. Go ahead and apply it, and we're going to go. All right, let me go ahead and get a similar question because I solved this one already. Let's see. All right, so this one here, barely noticeably different, but there it is. So we have limit, right? X goes to 0. We have x to the 5th minus 3x cubed plus 3x squared, all divided by, we have x to the 5th minus 2x squared plus 4x. If I just do my direct substitution, right, just plug in 0, we have 0 to the 5th minus 3 times 0 cubed plus 3 times 0 squared. I probably won't go through and do all the powers of zeros because it's obvious that they're 0. We have 6 times 0 to the 5th minus 2 times 0 squared plus 4 times 0. If we go through and run this, right, calculate this out, you're going to end up with 0 over 0. Hey, that's an indeterminate form. So we're going to apply L'Hopital's. How do you do that? So we're going to apply LH, okay. And what we're going to do is we're going to take the derivative of the top and the derivative of the bottom. Now, I'm going to kind of emphasize, like, we're not taking the derivative of this function. You're not doing a quotient rule, okay? It's derivative of the top, derivative of the bottom, independent, okay? No quotient rules. Well, you might have a quotient rule if there's a fraction in here somewhere, but you're not doing a quotient rule over the whole function, okay? So what that's going to look like, it's 5x to the 4th, right? minus 9x squared plus 3 times 2, that's 6x divided by, and then we have 30x to the fourth, okay, 4x minus there, and then plus 4. When I plug in my zeros here, we get 0 minus 0 minus, or plus 0, so we get 0 minus 0 plus 0, so we get 0 on the top. We have 0 minus 0 plus 4, we get 4 on the bottom. This is not an indeterminate form. This is just 0 over 4, which is 0. So my limit here, okay, this whole limit, this equals 0. So limit, limit as x approaches 0 of my top function divided by my bottom function, that's these two, this whole thing equals 0. You don't have to be quite this formal. If I just see that on your page, I'm going to be happy. Provided I see this on your page, so you checked, you're having indeterminate form. So that's good. I'm happy with that. Okay. So that's how you apply L'Hopital's rule. Right? So what we're doing, taking the derivative of the top, taking the derivative of the bottom, going with that, calling it good. Okay. And then moving on to the next problem. Okay. Again, I'm going to grab a similar question because I don't want the same one. Did you not give me a similar question? You did not. Barely. Okay, we span the range from A to A here. So we have limit, right, as x approaches 0 of e to the x minus 1 rather, divided by x to the 12th. Okay. If I plug in 0, e to the 0 is 1 minus 1 divided by 0 to the 12th power. That's 0 over 0. Hey, what do you know? We have an indeterminate form. Okay. Not all of them do. Okay, but we have indeterminate form here, so we can apply. So we have indeterminate form. We're going to apply L'Hopital's. So LH here. So we have limit as x approaches 0. Now look, the derivative of e to the x, e to the x. The derivative of x to the 12th is 12x to the 11. If I plug in my values here, right, we have 1, e to the 0 is 1, divided by 0. This is not an indeterminate form. Okay, as x is going to 0, right, this e to the x part, this is bounded by 1. It's not going to get any bigger. But this is getting smaller and smaller and smaller and smaller and smaller. So 1 over a very, very tiny number raised to the 11th power, right, this is going to go to infinity. So technically, we do not have a limit here because if it's not infinity, right, if it is infinity, it's not a number, right? It's just going up like this. So this does not exist as a function, okay, or as a limit rather. So we have to be careful about that. You can't just, cavalierly write down infinity. Sometimes you can, but they usually give you a hint. It's like, if it's infinity, say so. In this case, they want us to be really strict. This does not exist, so we'll go ahead and check, and we'll move on with our lives. Okay, so just be really careful. You're probably going to get this wrong a few times because even though you're thinking it's infinity and you're going to write down like infinity here, you can't do that. It's got to be does not exist, okay, except when it isn't. Okay, and I'm sorry about that. Your book is so, we're a little, we change our mind a lot with this. Okay, so let's go ahead and get some other problem. So we're here. All right. So what are we doing here? Page. All right. So in this case, right, we have limit as x goes to 0. We have e to the x up here divided by 5x cubed plus 3x squared minus 8x. If I plug in 0, e to the 0 again, that's 1. Plug in 0 on the bottom, that's 0, but this is not an indeterminate form. You can't use L'Hopital's here. Okay, so what's going to happen is, right, again, as x goes to 0, e to the 0, right, is 1. It's bounded. So this is a maximum here of 1. Whereas again, this is getting very, very small. And 1 over a very, very small number, we end up going off to infinity. So in this case, again, it's like, nope, not going to work. Okay, it's not L'Hopital, so we're just stuck with it does not exist because it's kind of like 1 over x. It just gets really, really, really big. Okay, we'll go on. Okay, so they will try to trick you. Okay, this is why it's important. You have to check to get credit for these things. If you don't, I'm just going to mark it wrong. So double check you have indeterminate forms first. Write it down. Okay, let me know you checked. Okay, now we can go on to the next part. Okay, so this is limit as x approaches 9 root x minus 3 x minus 9. Okay, so if I try to plug in 9, right, we get the square root of 9 minus 3, and we have 9 minus 9. Hey, what do you know? We end up with 0 over 0. That is an indeterminate form. So we can use L'Hopital's here, okay? So I'm going to rewrite it. So we have x to the 1/2 power minus 3 divided by x minus 9. So if I take the derivative of the top here, right, that is 1/2 x to the negative 1/2 times the chain, but it's just times 1. The derivative of 9 minus 3, 0. Okay. The derivative of x, 1. The derivative of 9, 0. So all we have left here is like 1 over 2 times the square root of x. If I plug in, x goes to 9 here, we have 1 over 2 times the square root of 9, which is 1 over 2 times 3, which is 1 over 6. There are other ways to solve this, and those are always legitimate too. You don't have to use L'Hopital's. You can use other methods. Okay, not the box. You can't do this. Okay, you can't just like count down to where it is and then count back up. And like, oh, it's the middle one. No, you can't do that. Okay, but you can use if you wanted to factor this, you could do that. Oops, I don't want to do that. I want to erase everything. And what do you mean by, can you factor that? You sure can. This is the square root of x minus 3. And this is actually the difference of 2 squares. Oops, not that one. Just this. Okay, it's kind of hidden as a difference of 2 squares, but it is a difference of 2 squares. You could say this is the square root of x minus 3, the square root of x plus 3. These guys cancel, so we're just left with 1 over square root of x plus 3, limit as x goes to 9, was it? So we have 1 over the square root of 9 plus 3. So this is 1 over 3 plus 3, which is 1 over 6. Okay, so you didn't need to use L'Hopital's on here, but it's probably an easier problem to do with L'Hopital's than not. So I would recommend L'Hopital's. L'Hopital's is very, very powerful. It's easy to misuse it because you have to check, and that's what you're going to forget to do. But it is a very, very powerful method to evaluate limits. So why didn't they show me this in Calc 1? Because you didn't know derivatives yet. Okay. So let's see here. That was next. All right. I guess I could have done a similar question, but that was those are pretty straightforward. Okay, these are really nice problems to pick. All right. So we'll go on to our next problem here. Oops. Whatever. Okay. All right. This is where it starts to get a little tricky. Okay. So I should leave you here. No. Okay. Limit as x goes to 2. Okay, we have the square root. Can I write the square root of x squared plus 12 to the 1/2? Because I know we're going to be taking a derivative soon, so we're going to need this. Minus 4, all divided by x squared minus 4. If I plug in 2, right, we get 2 squared plus 12, 1/2 power, minus 4, divided by 2 squared minus 4. think the bottom, it's pretty easy to see, like, hey, that's 4 minus 4, that's 0. Okay, the top, right, we get, let me go ahead and do it this way to evaluate so you can tell what I'm doing here. So this is 4 plus 12, 1/2 minus 4. What is 4 plus 12? 16, right? So this is the square root of 16 minus 4. Oh, we got a 0. So it is an indeterminate form now. Okay, so we can go ahead and say, well, it's indeterminate form because we got a 0 over 0. 1 over 0 doesn't cut it. Okay, so indeterminate form, use L'Hopital's. Okay, it's helpful for your reader to say you're applying L'Hopital's or you're going to use L'Hopital's. That way they're going to, because all of a sudden things are going to change and people are going to, what happened? We use L'Hopital's. Okay, so leave like a little trail of breadcrumbs, like what you did. Okay, so we have the limit, x goes to 2. Now we're taking this derivative. So this is 1/2 x squared plus 12 to the negative 1/2, right? Because that's the derivative of the square root function, times the chain. What's the derivative of the inside? It's 2x plus 0. Okay, derivative of 4, 0. So we're going to divide by 2x, and then we don't have anything else here, right? So we're going to simplify this a little bit before we apply L'Hopital's again. Does 2x's cancel? They sure do. Okay, so what are we going to end up with? We're going to end up with 1 over 2, that's this 1/2 because it's send it to the bottom, times the square root on the bottom, square root x squared plus 12. Now, if I plug in my 2, what happens? So we get 1 over 2 times the square root, 2 squared plus 12. Okay. Yeah. 2 squared plus 12. So that is going to be 1 over twice. Okay. And then we have 4, right? 4 plus 12. What is 4 plus 12? That's 16. So we have 1 over twice the square root of 16. So that's, right, that's 4. So we have 1 over 2 times 4. This is 1 over 8. And then we're all set. Okay, so here we're just going to hit then 1 over 8. Oops, not 18. 1 over 8. 1 over 8. Okay, and that's going to be my answer for something like this. Okay, so that's how you use L'Hopital. That's what's going to go on here. Okay. Okay, so what question? Really? Your similar question was the same damn question. All right, maybe there was a 2 here. I don't remember. Okay, so again here, we have limit as what? Limit as x goes to 0. Okay, we have 4 plus x times the natural log of x plus 1 divided by e to the x minus 1. So if I plug in a 0 here, right, we're going to get 4 times natural log of 1. What is the natural log of 1? That's 0. So 4 times 0 is equal to 0. E to the x, e to the 0 is 1. We have 1 minus 1 divided by 0. Hey, it's an indeterminate form. Or apply L'Hopital's, okay? And then we have to take the derivative of the top and the bottom. So the top, this is going to be a little messy because what is this, right? 4 plus x times natural log of x plus 1. There's a times here. There's going to be a product rule. See, this gets a lot more fun, right? So the product rule, we need the derivative of the first, right? So we're going to say, let me go ahead and draw this all the way out. So we have 4 plus x derivative times ln x plus 1 plus 4 plus x times the derivative of natural log x plus 1. Okay, So we're just working on the top here. Bottom is a pretty easy derivative. Okay, so here the derivative of 4 plus x, that's just 1, right? Derivative of 0, this derivative of 1. So times ln x plus 1 plus 4 plus x. And then the derivative of the natural log function, right? This derivative is 1 over x plus 1 times the chain, but the chain is just 1. And this is divided by, okay, this is divided by e to the x. Okay, the derivative of -1 is just 0, so just e to the x here. And of course, we have our limit, x goes to 0. All right. So applying, just checking it, okay? We have natural log of 0 plus 1. Dang it, I don't know what I'm pressing to make that happen. Plus, and then we have 0 plus 4, right? X is 0, divided by 0 plus 1. This is not 0, okay? It's 4 plus 0, 0 plus 1 here, okay? Because we're applying our limit. And then dividing by e to the 0, which is 1. So natural log of 1, that's 0. I evaluate this, it's 4. And we evaluate e to the 0 is 1. So my answer here is just 4. And that's how we're going to do this. Right? So we're going to need a, it's a value, and 4. Okay. Check, be done with it. Okay. So that's what you're doing with L'Hopital's here. Okay. I think I can do like 1 or 2 more here before we have to take a break. Okay. So this one, right? We have limit as x goes to infinity. So we have the natural log of e to the x plus 5 divided by 3x. Put in your favorite biggest number if you wanted to kind of check this, okay? Like 1,000,000. Better yet, Avogadro's number, right? 6.02 times 10 to the 23rd. Put that in and see what happens. So this is going to be absolutely huge, but the logarithm of a huge number, like look at the graph for logarithm. You all remember the graphs for logarithms? Okay, if not, that's okay. But it's just going to look something like this. The bigger you go, the bigger this is going to get. Think about taking log of 1,000,000. It's going to be 6. This log, not natural log, but they work the same way. Think of a trillion. It's going to be 9. Think of a Google. It's like 1 times 10 to the 100th or something. So it's going to be 100. So as much as you want to keep going, this will keep going. This will rise bigger and bigger and bigger. Okay? If you wanted to check it in the calculator, you don't trust yourself. I'm like, I don't remember what the graph looks like. That's okay. So what we're going to do is we're going to go through here. I'm going to make sure that my mode is function because there's other kinds of graphs you can make. Okay, so we're on function here. So quit. So what I'm going to do is say y equals. Okay, we can clear this. Okay, so y equals, and we're just going to type in natural log. And this button here is going to give us an X. Okay, you don't need to close the parentheses, but we'll just do that. And enter. Oh, and then we want a graph. All right. What I'm going to do, because that's a pretty crummy window, because I was using it for something else, we're going to go to the window. What's the lowest value of X you want? That looks okay, 9 to 9. But I want to do like, how about a -9 here? In a positive. Now, the -9 on the y was my choice. You could have picked -10s and gone up to 10. Okay, the same thing with these pieces. These were arbitrary, but since I have an idea, right, we don't have any negative x's. We could have left this to be 0, -1, that's fine. So you want to make the window just a little bit bigger than what your graph is going to be. Okay, so that you can actually get a good picture. Okay, so this is too big of a picture, but I think you'll get the plot. Okay, so it's going to go down, but it's hard to see that there's an asymptote here. It doesn't actually connect to 0. It just keeps going further and further and further down. Okay, so that's what natural log looks like. Okay, just to give you an idea. You still have to know, like, it doesn't connect. Okay, it does not connect. There's an asymptote here. So you have to have some idea when you're doing this, but this will help you get an idea of what the graph is going to look like. So this is going to go off to infinity, right? And 3 times x as x goes to infinity, that's also infinity. So this is indeterminate form. Okay, and now let's have a look. All right. So yeah, it's indeterminate form. We're going to apply L'Hopital's on it. Okay. So how do we take the derivative of the natural log function? Right? The derivative of natural log is 1 over whatever in the natural log. So we get 1 over e to the x plus 5, but we have to multiply by the chain rule. So we need to take the derivative of e to the x plus 5, and that's just e to the x. Okay, divided by 3, because the derivative of 3x is just 3. Okay, so we've got a mess now. We've got e to the x over e to the x plus 5 divided by 3. I'm going to do that to make, I only want one fraction. Okay, so we have 1/3 e to the x over e to the x plus 5. And it still kind of looks like it goes to infinity, but we're going to apply a different rule that you learned in Calc 1. We're going to multiply by e to the negative x over e to the negative x. Okay. So what's going to happen here is we get 1/3, what's this one? E to the x times e to the negative x, that's 1. And we get 1 minus 5 over e to the x, or 5 times e to the negative x. Okay. As this gets bigger and bigger and bigger and bigger, right? This 5, yeah. Let's go with this. Okay. As x gets bigger and bigger and bigger and bigger, right? We're going off to infinity. You plug in any value you want in here, right? Plug in 1 minus 5 e to the negative 10. Okay, it's going to be really close to 1, right? E to the negative 10 is a small number. It's almost 0. So we're just going to keep getting bigger and bigger and bigger numbers here. This 5 times e to the negative x, this is going to drop out because it's going to be almost 0. So we have 1 divided by 1 minus something that's really tiny. Just get 1. There's 1/3 out in front. So 1/3 times 1, that's equal to 1/3, and we're good. Okay. The reason why you would not want to use, say, L'Hopital's here is it's an infinite loop. Every time you take the derivative of e to the x, what do you get? You get e to the x. So we would do this multiple times, and we just get e to the x divided by e to the x, e to the x over e to the x, e to the x over e to the x, and so on until you die of old age. So we're not going to do that. I mean, you could use it one more time. That would have been fine. Right. But then you would get 1/3 e to the x over e to the x. And you could probably, at that point, you could probably see like, oh, that's just going to be 1. We don't have to care about this. So it's just 1/3. Okay, so there's a couple of ways to get around that and reason yourself through it, but those are 2 of the ways you could do that. Okay. So, oh, we got 1/3. Sorry. Okay, next. I should have asked for a similar question. Okay, but you can see that there a lot of them are going to be very similar. Okay. All right. Maybe, oh, say the best score, whatever. All right. Now we get to the tricky one. Okay, so this one, this one's going to be kind of tough. All right, and part of the reason it's got the natural log of a fraction, delightful. Okay, part of this is because we're going to have to do this more than 1 times. Like, how do you know? Like, I've done the problem before. It's terrible. Okay, there's a lot of stuff you got to keep track of. So if I say limit as x goes to 9 here, okay, of 2x over x minus 9 minus 2 over ln x over 9. Okay, so if I plug in the 9, right, we get 18. That's nice. Over 9 minus 9, that's like infinity. Minus, this is also a 0. So we get 2 over, there's an infinity here. This is indeterminate form. Okay. So what we're going to do is we're going to combine this function. So there's two fractions we could deal with, right? We're just going to add the fractions up and see what happens. Now, this, right? This is panic inducing because natural log of a fraction is like the worst, right? So do you remember a natural log rule that said we have a over b and how this is natural log of a minus natural log of b? Of course you do, because you remember your rules of logarithms for all time after you were taught them, right? Of course you did. Just to refresh us, AB is equal to natural log of A plus the natural log of B, okay? You really should hang on to your rules of logarithms. They really will make your life a little bit easier when you have to deal with them, okay? So the way I looked at this problem was to say, this is going to be terrible. So let's do 2x over x minus 9, okay? And then minus, okay? And then what do we have here? We have, actually, it's going to be like a 0 minus 0. No, it's not. It's terrible. And then minus, and I put 2, and instead of that natural log, I said, this is the natural log of x minus the natural log of 9. Okay, it's still a fraction. We still got to get common denominators. We got to do everything else. But I would rather look at natural log x minus natural log 9 than natural log of x over 9. Okay, this just struck me as an easier way to go. But if you wanted to keep it this way, that's just fine. The book does it this way. If you go through the show me an example thing, they all do it this way. They don't convert. I just found this to be a little bit nicer. So getting my common denominators here, right? We have 2x times ln x minus ln 9, right? Minus twice x minus 9 divided by, and then we have x minus 9 ln x minus ln 9. Don't multiply this out. It's not worth your time. Okay, we could multiply out the tops. That's fine. That might be easier. So we have 2x ln x minus 2x ln 9 minus 2x plus 18. Actually, I think I will multiply them out because it'll be a little bit nicer a little bit later. So we have x ln x. You can't cancel this. Okay, it doesn't work that way. Minus 9 ln x, right? That's here. Minus, oh, this, okay, we're good. Minus x ln 9. Okay, these are all different. Okay, the x is on the outside of the natural log, down on the inside. Okay, so x ln 9, and then finally plus, because minus times a minus, 9 ln 9. All right, so again, we plug in 9. Okay, we get natural log 9, that's 0, 18, negative 18, positive 18, so those are all zeros. Right, we have 9 ln 9, 9 ln 9, 9 ln 9, and then 9 ln 9. Okay, so all of these turned out to be the same when x was 9. Okay, so we still end up with a 0 over 0. I'm only checking that just to make sure we still have a form. Okay, that wasn't that necessary because we checked it here at the beginning. And we did some algebra, but we still have indeterminate form. So let's go ahead and apply L'Hopital's. All right, we have 2x times natural log x. You know what that means? It means we get to do a product rule. So the derivative of 2x, right, the first, that's twice, times ln x, okay? Plus 2x times the first times the derivative of the second. What's the derivative of natural log? It's 1 over x, okay? So this is the product rule just off of this first bit here, okay? ln 9 is a constant, 2 is a constant. So we just take the derivative of x times a constant, we just get twice ln 9. Minus, take the constant, take the derivative of 2x, we get 2. Okay, and then the derivative of 18 is 0. Okay? So for the bottom, right, again, we could do a product rule. So the derivative of the first here, just x, is 1 times ln x plus the first x. What's the derivative of ln x? 1 over x. So this was the derivative of the product of this piece. Minus 9. What's the derivative of natural log x? 1 over x. Okay. Minus x times the derivative, well, times x times a constant. Okay? Minus x times a constant. So that's just minus ln 9. Okay. And then 9 ln 9, right? 9 natural log 9, that's a constant. So that derivative is 0. We don't need that. Okay. So let's regroup just a little bit. So we have 2 ln x plus, hey, these cancel, don't they? Plus 2 minus 2 ln 9 minus 2. Okay. And then on the bottom, we're going to have ln x. X divided by x is 1. Minus, I've got 9x to the negative 1. I'm suspecting I'm going to take a derivative soon. So that's how I want to write it. Minus ln 9. Okay. Now, if we check, limit x goes to 9. Okay. What are we going to have here? We're going to have this is just, we're just checking here. We're going to hold on to this. And here's my check. Okay. What might be better? Let's go ahead and put the check in a good green. Yeah, that's a better green. So we're just checking. Go back. So we have 2 ln 9 plus 2 minus 2 ln 9 minus 2. All right. And on the bottom, we have natural log of 9 plus 1 minus 9 over 9. That's what x to the negative 1 means, right? Minus ln 9. What happened? We got some canceling. We got some oh, that's 0. Let's hope for the best. 9 minus natural log 9, right? These guys cancel. Plus 1 minus 1. Oh, look at that. It's 0. We can use L'Hopital's because this is indeterminate form. Okay, I'm really sorry about the blinking. So we went back, we're going back to our result here. Okay, we could clean this up a little bit. We have a 2 and a negative 2. We can get rid of that, right? That's just going to be 2 ln x minus 2 ln 9. Right, so we have 2 ln x minus twice ln 9. That's my top. Okay, so we're just going back to the original. We didn't apply a limit yet. Okay, now what happens on the bottom? Okay, we had ln x. Yeah, there's not a whole lot we could do here. So we just have ln x plus 1 minus 9x to the negative 1 minus natural log 9. So the bottom is still kind of a pain in that we have this. Okay, minus ln 9. But because we had an indeterminate form, we can go ahead and apply L'Hopital's. Okay, so the derivative of the top, right, that's just going to be 2 over x. Okay, minus, what's the derivative of this constant? 0. The derivative of, I'm sorry, this wasn't natural log 9, this was natural log x. Right, because we are here. Right, natural log x. What is the natural log x? That derivative, rather. 1 over x, right? Derivative of the constant. Okay, this is going to be, take the derivative here. So that's going to be a plus 9 x to the negative 2. Okay, and then minus a constant, just there. So let's go ahead. We can plug in 9 again and see what happens. Okay, so we end up with limit x goes to 9 of 2 over 9 over 1 over 9 plus 9 over 81. Okay, so this is 2 over 9 divided by 1 over 9. What is 9 over 81? 9. So we end up with 2 over 9 divided by 2 over 9. I think everybody can tell that is 1. Okay, so that's how we're going to go through and make sure that we got, that we don't have an indeterminate form anymore. We're done. We got a value. Okay, so equals 1, and we'll check, and there we go. This was I'm not going to lie to you, this was a hard problem. Okay, part of the reason I went and did this with the beginning was because I knew I was going to mess up the chain rule when I dealt with this natural log of x over 9. So I tried to make sure that I didn't mess it up. The other thing is taking this derivatives here, if they're trying to do just constantly doing product rules, I knew I was likely to mess that up. So I strung it all the way out to minimize my error. Okay, so don't be afraid to do that. Okay, this is why we taught you all the algebras, because you would have the tools to be able to untangle all of this stuff and deal with it in smaller chunks that you could manage. Okay, so that's what happened here. Okay, so this is a really tricky one. I can't say I wouldn't put this on an exam or on a quiz. I'd feel a little bit bad about it. Okay, so if I was going to do something like this, I'd probably put a part A, right, and then make this one part B, so they're each 3 points. So that way, if it's going to happen, if you fell completely apart on this one, it's going to be 1 out of 3. But the part A is going to be hopefully something easier. Definitely be an easier problem. Okay, so it would pick something, something like this. This would be a nice problem to do. Like, this is a really good quiz question because it's really straight. Actually, it's not a great quiz question because it's too easy. But if I'm in a good mood, I'm like, oh, I gave them one really hard one. I should probably give them an easy one, like what we were just talking about. Like if you have a really hard one. So what I would expect is you would get a 3 out of 3 here. When I add it up, you get a 4 out of 6 for the problem, which gives you an overall as a C, because I knew this one was going to be a problem. Okay, so trying to mitigate and say, well, let's not completely destroy your grade. Let's give you an easy one, balance it with a hard one. So you get the easy one, maybe you get a little bit on the hard one, but overall you get a C for that problem. So 4 out of 6, so that it doesn't completely tank you. Okay, so be aware that this could be on the table, but I would feel bad about it. This could be on the table, but I'll feel bad about it in the opposite way. Okay, so with that, I'm going to let you go. I will see you in the next video. We'll try to go through some of the other problems here. I know they're tough, but some of them are, some of them are not. Okay, so I'll see you next video. Thank you.